Good afternoon. We've said before that we can derive a lot of thermodynamics from statistical mechanics. And what I'd like to do today is we're going to talk a little bit about thermodynamics, or at least kind of get there. But the way we're going to get there is to talk about interaction between two systems. So between two macroscopic systems. What we'd like to do is, let's talk about a system of interest. We'll call that system A. And A, when I want to understand this system, I would create a system or an ensemble of systems exactly like A. And let's look at some mean values that we might get. So for example, if I have an ensemble of systems that have a mean energy, we'll call it double bar E1, so that indicates an ensemble average. Let that be the energy of system A. If I had entities that concern external parameters, maybe things like volume or pressure or an external electric field or magnetic field, let's lump that energy, that mean energy, associated with this system into some V1 double bar. So that's kind of what we might think of as maybe potential energy terms, if you like to think of it that way. Finally, if I put this system A in contact with a much larger system, maybe we can call that a heat reservoir, for example. Or I might talk about the mean energy of the heat reservoir, we call it E2. And so if I were to look at the mean energy of this whole combination, the ensemble, where I would have a whole bunch of systems like A in contact with a whole bunch of reservoirs like the larger system, I might look at a total energy of that combination as E12. That's the total energy, and it would be just the sum of the energies of those systems. So it would be E1, that's the energy, mean energy for A. E2 would be the mean energy for the reservoir, and then I would add to it this sort of like potential energy term that has all the external parameters in it. Now, each member of this final ensemble is itself an isolated system. So I can look at system A in contact with the reservoir, many, many, many systems just like it, each of them being isolated systems. That being the case, we know that if it's an isolated system, any change in the total energy of the system must be zero. So in other words, energy can go back and forth between the reservoir and the system. Maybe it can be changed from one type of energy to another, but the total energy of each closed system, the change in total energy will be zero. Total energy itself has to be a constant. So let's do the following. Let's simplify our terms a little bit. Suppose I want to define my mean energy in system A, or system 1, as delta E. I can look at, in this case, I'm going to call Q double prime any change in energy of the reservoir. So if the reservoir gives some amount of thermal energy or heat to the system, that would result in a decrease in delta E2, such that we can say in total, the total change in energy, which we could call delta E double bar, which is delta E in this case, double bar 1 and 2, is just going to be equal to Q minus W. How do I say that? Well, in this case, if I look at Q double bar as the heat lost by the reservoir, I can talk about work as being related to any external parameter that's associated with system A, then what I have is, of course, a representation of the first law of thermodynamics. It's just a restatement of the conservation of energy. So what we say in that case is, if I'm talking about the, let's say the energy lost by system A would be equal to, or energy gained, would be equal to the heat that's given to system A minus the work that system A does. Okay, that's simply a conservation of energy, and this, of course, is what we call the first law of thermodynamics. Now what we want to do is let's look at the interactions between macroscopic systems a little bit more carefully. We can think in terms of two types of interactions. Thermal interactions and mechanical interactions. There's a third type that we're going to talk about later called diffusive interactions, but we're going to wait on that before we introduce that concept. So let's think of it this way. Suppose I have a macroscopic system, and suppose I can measure some independent external parameters about that system. Maybe these would include things like volume or pressure or other external quantities. These external factors are going to affect the equations of motion of the system, and thus are going to have some term in the Hamiltonian. So, that being the case, we're calling these guys external parameters. As I said, things like volume of a gas, or maybe the applied electric field, or applied magnetic field, other things. The energy levels of the system will depend upon the external parameters, but we'll get to that in a bit. So if we were to prepare an ensemble of systems, a representative ensemble to represent this system, all the systems in the ensemble would be characterized by the same values of external parameters and the same total energy. And there may be